Okay, so today's topic is about digital sensor interfaces. Sorry, that was not on. But anyways, I'll start anyway. So we are talking about, in particular, three industry standard digital interfaces generally used on, say, basically any sensor. And basically, we are talking about that part. So let's see. Let me plug my pointer. So that part, digital communication between sensor and our black box, which is a microcontroller. And basically, next we will also visit briefly this one. But the next topic would be about wireless communication and stuff like that. So basically, there's absolutely no mystic around that connection anymore. But still, the beef is today on the digital communication. All the sensors are becoming digital, more or less, so that basically you can use almost any microcontroller environment to get that essential data in. Okay, for example, you can see that one, for example, on the Raspberry Pi. It does not have any A to D converters. So it cannot take any analog data other than voice. I think it has a voice input. Does it have audio codec? Maybe, but anyways, it doesn't have any A to D converters, unless you use your external A to D converter and have the digital communication between that one. All right, so a couple of things here. Two different types of serial communication lines are used. One is asynchronous, and then basically there's also the synchronous serial communication. The only difference between those is that synchronous has a clock. It has a data transfer clock, which basically means that you can also have irregular the data clock. But asynchronous, you must have basically sampled digital data there. For the asynchronous, the data transmission, there's a term UART, which is a device which basically handles the asynchronous signals and sends and receives those. So UART is basically acronym for Universal Asynchronous Receive Transmit. It's a peripheral function. Well, nowadays it's inside of these microcontrollers. They have been there for a while, from 80s. Basically, as long as we have had terminals, we have had this serial line communication. And that's common technology, and all you need to do for UART, you just basically tell it what to do, and it does the data transmission itself for you. And in PSOC, there are basically different kind of modules. There are separate TX and RX modules, so transmit and receive modules, if you need only one directional, but if you need two directional data, then of course you need the full UART. Okay, and basically those same or very similar blocks are also used on other data transmissions, also the synchronous transmission. The difference here is basically just where do you synchronize the signal? Inside or using an external data clock? Okay. A couple of terms which are historic. There used to be basically two different kind of devices on asynchronous serial line. One is DTE and one is DCE. So basically DT is data end terminating device, or data terminating equipment, yes, meaning the old-fashioned terminal for mainframe. That was DTE. And when PCs started to come in, they were also connected to the mainframe. So this, after that one, also defined as DTE systems. And basically there's only one practical circuit on the DCE, which is the modem. And the difference is only on if it has a male or female D connector, which we don't have anymore on those computers or anywhere else. But anyway, so practically almost all devices or systems are defined nowadays with they would actually the signal is defined so that it looks like it was DTE equipment, which means that in order to do data transmission between two devices, well, you have to cross the transmit and receive lines, of course. One transmits, another receives, another transmits, one receives. Okay, that's actually true if we are bridging, if we are using a USB bridge, the device between that piece of one and the computer. Okay. Anyways, on this asynchronous data transmission, there are some parameters you have to fix. The most important is the bit rate. Without the bit rate fixed, you cannot actually see much of data transmission happening. Then, or well, it'll be funny bits, only funny bits showing up. How many data bits? That's also something you need to fix. The most common is 8 bits. On the bit rates, there are no general the bit rate that should be used on the first place, but say 9,600 bits per second or 19,200 bits per second seem to be the most common ones. But of course you need to check that from the data sheets. Okay, then the parity check. That's probably the reason why this serial line standard came alive, was because there was a very primal way of checking if the data transfer was good or bad. That was a parity check. Simple parity check. So basically, if you have an even parity check, it means that if you have a even number of bits up on that data, then that bit is 1, otherwise 0, and then the odd is the number of odd. If that number is odd, then that's 1. So either even parity check or odd parity check, or then of course you can also neglect the parity check, so no parity. Okay, most commonly there is no parity check nowadays anymore. Lines are short, not anymore. say 300 meters or so. So RS-232 old standard supports 300 meters of per cable, and that was kind of the state of the art at one point before the someone noticed that you can actually this consistency on the quality of these telephone lines is good enough that you can actually use balanced data transmission. Okay, yeah, and then stop bits. Stop bits basically is just a pause between data transfers. That just separates one data transfer from the other one. So if the first doesn't go well, then basically there's a chance that the second one starts okay. So that kind of parameters. And then there are also some other parameters from the old ages. There was also the carrier detect for modems, ring indicators for modems, and even some serial lines has the second serial line on the next to it. And then there was a handshaking lines. I hope that you never actually bounce into that kind of things. Then you will be basically dealing with ancient technology. Good old technology. No, everything is better now. Take my word, I'm a dinosaur. Okay, few words about the serial communication between that black box and PC. Okay, while the previous one basically was between the or in general the asynchronous transmission, there's a UART, but that RS-232 line is that 9-pin port on PSOC. By the way, that's female, so it's actually DCE device pin out. Okay. But anyways, there's a standard, and you can basically have run the data transfer with only 3 lines. One is of course ground, and then you need either or both transmit data and receive data lines. You may actually also have all sorts of handshaking signals, and there are those 6 standard handshaking signals available on that standard. Okay, and basically the handshaking signals were on the area when the data transfer was faster than the process. Currently, we and then those say first in first out registers were hard to implement on silicon. Everything was done by hand, especially the silicon engineering. But anyways, so there are those handshaking signals. Now, if you need handshaking, meaning that if you are using on serial lines so fast communication speed that your receivers, the buffer actually starts filling up, you can actually now use the quite kind of industry standard, the Control S, Control X, I think it was. Or Control S, Control T. Anyways, sending the receiving end actually sends a character Control S to the transmitter, and transmitter should start pausing. And when it's ready to receive again, it's Control T, I think. But that you can find it from the some ancient books. Okay. Voltage levels for historical reasons, minus 15 to minus 3 volts is logical 1 or idle signal, meaning that there is nothing, no data transmission there. So it's negative. So it's basically inverted in that sense. Then plus 3 volts to 15 volts is logical 0. Okay, for say any microcontroller, that would be a little bit difficult to handle. The voltage levels are not on the same as the TTL levels, standard the logic levels. Most of processors which have a serial port there, they can actually tolerate those voltages as input, and then, but of course then they send from 0 to some to the power supply voltage output, and most of the input buffers actually can use those signal levels too, if it's say a 90s technology. Okay, this piece of board actually has a standard driver and those standard signal levels. All right, so yeah, D connector, either 9 or 25 pins. 25 pins is again a little bit older technology than 9. I haven't seen 25 pin equipment since 90s anymore. And then there's the most common parameters for transmission, 9600, 8 bits, no parity, one stop bit. Okay. If you take a look at your computer, there shouldn't be any RS-232 ports anymore. If it does, change your computer to a little bit newer one. So there are no RS-232 ports, but on say Windows and Linux, there is also the drivers for virtual COM port. It's basically a USB port can act as a the logical device looking like a standard COM port. That is because we have plenty of instruments available which have the serial line only, no USB bus or any other bus. So this is the easiest and cheapest way of connecting an instrument to a computer. And basically when you put that kind of USB device, so USB USB COM port adapter, the computer recognizes it, and since it's USB device, it automatically installs the drivers, and then you can start using it, putting parameters in and so on. So it, for the computer point of view, it's exactly like any COM port. For microcontroller, it looks like any serial line. Only thing that you need in between is that small device that makes the translation. Okay, and we will be using, well, next week, not this week. This week, try to go as far as possible on this second exercise, or if you have still something patching up on the first one, do that one. So next week on laboratory, we'll start with the tutorial for that, the lab 3. Okay, so next week we will see that another kit. There's a very cheap piece of 5 prototyping kit. You may have used that on first year project, some sort of robot project. I think you have used it. It's just like stick like that one, a green stick like that one. Okay, I have seen those on first year projects. Oh, okay. Yes, yes, yes. That was the 5, which is the stick kind of thing. Yeah. So it actually has the it's programmed using that USB port there, but it's also a USB bridge. It looks like a serial port if you just connect the pins. Okay. Yes, virtual COM port. And that's basically what we will be checking next week exercise. But back to the beef again. So the whole idea of having serial buses for these sensors is just to save some the electronics design space, so the circuit board space, and basically simplify them, and in principle you can even have just wires coming from the sensor directly to this microcontroller board, and you can then distribute the wires where you want. If you had long analog wires and small signals, you would end up having problems with all kind of noise induced to those lines. Okay, so that way we have this kind of the buses overall. One good example in real life applications is the CAN bus, which is a serial bus, which also gives the power for those sensors and well, controllers, all kind of stuff what there is in a modern car. And well, it's quite robust system. Car is not the easiest place to put sensors. It's basically in Finland it can reach minus 50 degrees in Muonio, for example, and in summertime easily 60 degrees when it's on sunshine. Not in Finland though, but some other country. But you know, the same, these cars are sold in different countries. So the temperature range is huge, and then of course the moisture, super saturating moisture. Salt from both on the seaside, you can get salt on the air, and in roads you have the salt also. This is this corrosive environment. Then there's a motor that generates heat. You have sensors next to the heat source. Okay, not the easiest place. And okay, how much current actually it takes when you are cranking up the motor? It's hundreds of amps peak. So about 300 typically. Yeah, and vibration, everything is there. Excellent. It will be really fun to design my own car. I will start with the sensors. Okay. Some say serial line protocols. The simplest serial wire interface is actually OneWire device. It's OneWire is the name, but it requires the two wires. One which carries the data and one is the ground. It also is designed so that the data wire is also used to power up those sensors. Usually you don't need much power for any sensor technology. They are very low power in principle. So it means that basically even those, say 1 milliamp is enough to power up a OneWire sensor. Okay, and then there's some charge pumps and such kind of things to make sure that it doesn't die when the data goes to zero. But anyways, the OneWire, this hardware is very simple. It's just you connect all the sensors on, which are those slaves, into one master. That's not politically correct kind of naming, you know, master and slave. No, but well, what we do, well, this it's engineering. Yeah. Okay, devices and the master. Okay, so this master basically just initiates the transactions, and there's a well-defined, predefined protocol with quite strict quite strict speed constraints. So the clock rate should be exactly right, not just around there, that kind of things. But anyways, you can put a lot of sensors on that OneWire bus, and then just master just goes first. When you start up the system, it goes first and checks what kind of devices there are on the line. So it first goes through a protocol that defines all the slaves on that line. And after that, it can actually access each of those by their internal address. Okay. And actually, the address space is 64-bit, which means that when you are buying a or 2 or 3 or 5, actually up to say 120, I think was, which can be on the same line at the same time. It's quite small probability that you will find 2 devices with the same address. And I think there are still, I think there have been something like how many years now? 30, 40, no 30 years, about 30 years old standard, and they are still building, you know, making devices with a unique address. Okay, but in few years we are running out of addresses. I don't think that's a big problem, but anyways, so easy on hardware side, a little bit heavish on the software side, but on the other hand, it's very well standardized, which means that there's plenty of code already available for that one. So PSOC actually has OneWire, the master device to be used all with the OneWire devices. Okay, and that's about the power. So it basically you can build the you can use this data line also to power up the devices. On the other hand, if there's also external power, then well, you can use that one. And anyways, it's just the data ground, and then inside of that device there is always a small capacitor with the diode, so that if you are actually running this one from the data, then basically that circuit makes sure that there is always some power to the device. But okay, this is it also means that it cannot take too much power. If it's a higher power device, then you need to have external power supply. But it can also run with the so-called parasitic power. Okay, PSOC 1 has a OneWire module. Some devices and applications, okay, well, those are not too interesting, except we actually have this DS18 S20, or actually this, I think 22 plus, but anyways, it's a OneWire the temperature sensor made by Maxim, and that's our example on next week's exercise. Okay, so that was OneWire. The I2C. I2C stands for Inter-Integrated Circuit, originally defined by Philips, and we all know what Philips means. It means piece of excellence. Okay. And yes, I2C is still a trademark. So if you are making a device which is I2C compatible, you need to go through Philips manuals and get their certificate. But you can always call it two-wire interface, which does the same thing. And then you don't need to mention Philips at all. Okay, that was one of the ultimate hacks, meaning that if you can hack the signal, you can use it. Someone just, took an oscilloscope. The signal is very simple. The protocol is very simple. And just, okay, we have this two-wire interface. Okay, but anyways, so synchronous bus, 2 wires. This OneWire is, in principle, it's asynchronous bus, but it has a constant clock rate, meaning that's factually it is a synchronous bus. The synchronization is done inside of the circuits. But anyways, it's tomato kind of thing. So there are 2 wires on the I2C. One is for the data in and out, and one is the serial clock, which is run by the microcontroller or master. Okay, both lines are type of the open collector, meaning that it's held up by pull-up resistor to the power. Okay. Then there are 2 standard data rates, 100 kilobits per second and 400 kilobits per second. Anything other than that would be, say, 2-wire bus, which can anything. Okay, and when it's designed between 2 integrated circuits, it means that the bus length is relatively low. So it's not between the boards, it's inside of one single circuit board. And basically, when you have these pull-up resistors and open collector kind of drives, it means that any of those masters or slaves can set a state 0 into that line. So yeah, so as long as they are not talking all at the same time, basically the everything will be fine, which means that all the transactions again are started by the microcontroller master. So master initiates all the transactions. There's also it sets the clock signal for the bus. When the transaction starts, well, there's actually I think there's a timing diagram next. But anyways, okay. Then there is actually each device have 7-bit address. Okay, 7-bit is not enough, not much, but quite commonly you can set at least 3 of those bits yourself. They are external, fundamentally 3 pins that you can set either high or low and define the 3 bits from that one. So when you are making a design like with the I2C bus, you can always put there lots of different sensors, actually more than the bus can carry. So it has enough of address space. And the different devices, manufacturers and device type, they also have these 4 bits will be different in any case. Okay, but anyways, so master is telling what happens on the bus, And that's a typical transaction, how it starts. So that's a 1 byte payload. The start is marked actually such that those SCL and SDA are a little bit lower than they should be. So the higher is of course the clock. Fundamentally it's a high state on the beginning, so it's idle state. And if the master starts talking to the bus, then it basically first sets the data down while the clock is up, and then the clock goes down. That actually marks the this transaction start. So this here means start. Okay. This means actually stop. When the clock goes high and stays there, and the SDA goes high, that's stop. Okay, so basically this can be as long as needed. Meaning that one place where this one is used is with the EEPROM circuits on all kind of small devices, or actually the computer, those motherboards used to have, I don't know the current technology, but they used to have a separate EEPROM for the boot code. The BIOS was on the EEPROM, serial EEPROM, meaning that this is excellent for burst kind of mode data transfer. You can transfer data by one block from or one data block of the memory can be transferred either way in one single transaction. Okay, that was the start. Next basically is the forced one. No, actually that's not forced one. That's the address. 7-bit address. Okay. Most significant bit first, 7-bit address transferred so that you have a stable data, and then you go with the clock up and down, stable data, clock up and down, and so on. And 7 bits plus read-write bit. So that one tells, okay, is the master writing data, or is it actually expecting data be written by the device? The acknowledgement bit here means that that device, if it's there, it must set the acknowledgement down, so data down for one clock cycle. So telling, yes, I'm here. So there was basically a device that answers to that address. Excellent. That's a good start. At least one device started answered. Okay, and that one is followed by a command byte, or the data payload byte. And each byte, 8-bit byte, followed by listening the acknowledgement. And as many bytes as there are. Okay. And the end, the stop.
Could you repeat again the acknowledgement? Who's sending the acknowledgement?
It's always the receiving side is setting the acknowledgement bit. So on the write operations is the device, on read operations is the master. On the master side, you need to listen the acknowledgement on the or set the acknowledgement depending if you read or write. Okay. We were teaching actually I2C bus when it was quite young. Well, not young, but on early 2000, and we actually had this 8051 microcontrollers, and everything was done with the software. Now we have PSOX, which has modules and APIs. Okay, that's there's also transmit and received mode basically can be done. So fundamentally everything what I'm telling here is quite device dependent what kind of data communication it uses. But for example, here we have the DS1621, which is a one sort of I2C, the temperature sensor, I think, and it has that kind of system. So basically, you can also have, say, a command. So it starts by write payload, listening for acknowledgement, then repeat the start conditioning, which means that the device here, well, you need to also set the address, listen for acknowledgement, but then basically it's a read signal. So after that, read the data. That's basically speeds up the transmission a little bit, not much though. At the end of the transmission, it can stop. End of the transmission can be actually marked as either the not acknowledgement or end. But for this device, actually requires that in case of reading only 1 data byte, then you basically give NUC signal. Yeah, it can be used also for to stop the. Yeah, don't ask me. Ask this. This is actually 2-wire, 2-wire device. Yeah, DS. That's Dallas, which is nowadays Maxim, which is nowadays. Who cares? All right. Some I2C devices. Yeah, and then some. I got some TC75s, I think, just because it's TC74. Sorry, TC74 force just because it's easy to connect to that wiring board. Okay. Then there are, for example, accelerators, color sensor, real-time clocks. You just imagine a sensor. There is probably also I2C bus version of it. It's more common than OneWire interface. But okay, that's what Juho Vesanen used. We don't have those anymore. Okay. Then there's also kind of extension for the I2C. It's SM bus, system management bus. Okay. So fundamentally, it uses I2C, the signals. And for example, those intelligent batteries actually have the I2C bus there. Okay, there also is I2C buses in some of those memory cards. Just another interface. And yes, of course, I wouldn't tell you anything about I2C, or not that way, if it wasn't on PSOC already. Okay, there are different modules. One is software master module, basically. That gives you freedom of use any port pins for that transmission. Okay. Takes only some memory space, but it actually consumes quite a lot of CPU. Yeah, and cannot be used with background or with interrupts. Well, it can, but it doesn't work. Okay, then there's the hardware implementation, meaning that the this actually, one of those is directly the same hardware as the programmer, since actually that device programmer pins are I2C. It's SDA, SCL, and then there's also reset signal in addition to those I2C bus signals. And then another one uses block, hardware block. Okay, that's the same hardware block as the I2C hardware. But there's a master or slave interface, or easy I2C is slave only, meaning that you can make a intelligent device using from that piece of, for example, that Raspberry Pi doesn't have the A to D converter. You can plug in a signal using, convert it in a PSOC, and then just have the easy I2C slave interface, so that you can actually go on a Raspberry and read I2C bus from that address to get the A to D conversion signal. Very simple way to add AD. It's just few wires. Okay, and then some things that we actually go through the on next week tutorial. Then there's a SPI versus I2C. This, let's see. Okay. Another. These are a little bit in awkward order now. Anyways, there's another bus, just another. So first one is OneWire. It's a quite heavy protocol, but anyways, the software does it. And it's both ways kind of signal, and only one signal line. Then there's two-wire or the I2C, which is kind of a nice way of, robust way of transferring signal. There's a data line and the clock line, which are both pulled up by resistors and open collector outputs on the devices. Then we have SPI. SPI stands for Serial Port Interface. It's older than me. Yeah. Wow. Before dinosaurs, you know. What was before dinosaurs? Frogs? Okay, frogs. So basically, usually on microcontroller environment you can find some systems on I2C bus and another systems on SPI bus. SPI bus is nice because it can be very fast. Okay, flash cards or those SD cards, actually, those use SPI bus to transfer the data. Okay, so that's actually used in plenty of the fast speed requiring interfaces. And then of course audio codecs signal is usually with the SPI. Video codecs SPI. It can go up to say few hundred megahertz or megabits per second rates. Okay, I2C is slowish but on the other hand, then it also it's a address bus. SPI is not address bus, but the I2C is. So it's I2C is say nice for transferring small number of data from a lot of devices. For example, there are this SIM card interface. So SIM card has, yeah, I2C. No need for, speed there. And again, SIM, because of that address, it also brings a little bit more of the security on that one. Not much, but very little bit of security. You can lock a SIM card. Okay, you can, and it doesn't work anymore. Except you can hack it with the I2C. Don't do it. Okay, real-time clock. Yeah, if you need a clock that deviates from the real clock only, for example, less than 1 second a year, then you need a external real-time clock. And usual interface is the I2C. Temperature sensors, all kind of that kind of thing. So it said here typical mobile phone. Well, yeah, that kind of buses are actually in between the devices. Yeah, again, SPI devices. Hey, there's also TC74. Okay, TC74 can have either SPI or I2C bus. Okay, then there's a nice accelerator, SCA3000. We have few of those still laying around. That's one of those Murata sensors made in Vantaa. That's one of our partner companies there. Then there's the digital barometer, which was actually no, that is still on production. That's the let's see. Logo is start with F. Okay, but anyways, and then flash memory chips and that kind of things. And of course, there are these SPI memory cards. Okay, if I remember correctly, on the PSOC there is also interface for SD cards. However, SD cards also need the file system. Okay, so you need also the software for the file system. I think you can actually read and write from the those standard file system cards, but you cannot do the formatting of those cards on PSOC, if I remember it correctly. But anyways, usually you don't need. But if you need to save a lot of data on PSOC, you can actually do it. Yes, then radio modules. All sorts of radio modules. We will be using on our the radio communication. We are using the NRF24L01 Plus device, which is very simple, like that. It has SPI interface, and it's rather simple to use. There are something like 100 registers. You need to initialize few of those, and then basically you can do either the star the organization, the of that wireless network, or well, of course, point-to-point communication, or a broadcasting. Good, but we will be testing that device on the RF communication or wireless communication system. Okay, some network interfaces. Okay, plenty of these available. So if you really need to make a device that plugs into, the wired net, their devices available. This is definitely the easiest way to get connected to small processors like that, where you really don't want to have the IP stack yourself. You have to basically have a small dedicated device that does everything for you, connecting automatically to networks and that kind of things. And then you can actually, using these devices, you can then put any simple microcontroller like PSOC into internet, in wired internet. And yeah, there are also the similar Wi-Fi blocks available, but the wired they are cheap. All right, and then this should have been there before. So SPI, Serial Peripheral Interface. Okay, full duplex, meaning there is data transmission lines for output and input. Signals are the 4 ones, and okay, there's serial clock. Always this is driven by the master. And by the way, there's only 2 devices on this bus. So master and slave. You can put multiple slaves, so you can connect these serial clocks and MOSI and MISO to any other slave circuit, but then each of these slaves must have their own select signal. Okay. But anyways, so serial clocks needed, and basically only the device, well, the hardware actually defines how fast you can go on the serial clock. So fundamentally you want to go as fast as the slave or master can go on these clock signals. Most of the SPI slaves can do at least 1 megabit per second lines. They are not designed for slow data transfer at all. Okay, but you can. It can be even 1 bit per second in some cases. I don't recommend it. Okay. Anyways, the data lines: MOSI, master out, slave in. So simple, driven by master and read by slave, or listened by the slave. Another one is MISO, which is master in, slave out. So that's the way the master reads the data from the slave. And then the chip select. Okay. Most commonly the chip select is low active. But anyways, the good part is the speed, but the bad part is then you really have to read the data sheet. There's no other standard than this signaling that way. It even have 4 different modes on which way these signals are actually. Is it state active clock or edge active clock, or is it inverted, or variability. So read the manual. Okay. So so that's basically the thing. So having more than one, you need always different each of those slave devices must have their own individual select signal. Okay. The operation. Those are the modes. Leading, clock edge, clock non-inverted. Leading clock edge, clock is inverted. Trailing clock edge. So 4 different modes. Fortunately, I think it was mode 0 was the most common here. So usually it just starts working. And there are only 4 modes. You can always, trial and error at the end. Okay, but 4 modes, 4 operation modes. Yeah, and another thing. Okay, the protocol does actually, it's just a interface is defined. We still can have a big endian or small endian devices there. So most significant bit first or least significant bit first. Then also the word, if there are more than 1 byte, then which byte goes first. But those you need to check from the datasheet. Yes.
What will terminate which mode to use?
The datasheet of the device. And of course you may have different slaves there with different modes, and you're using one single transmitter. You need to change the mode for the device that you're reading. Okay. That's actually something that Juho Vesanen, he was here. Who knows Juho? You probably know. Smart, one of our best teachers ever. He's working now for the F-Secure and really enjoying his stay there. So it's a kind of dream job. Yeah. Too bad. But anyways, he did all kind of stuff here, including I was also acknowledging on this slides. So this is actual readout from a digital scope of 1 byte sent from the microcontroller, and those serial in, serial out. Okay. MISO and MOSI signals actually, but they're somehow marked like that. But anyway, so it's write enable, signal goes down. Why there's write enable? Okay. In addition to this, wait a minute. This signal is not correct. The clock and serial lines are okay, but there's no write enable. There's a chip select. Chip select. I see. The write enable actually means those bits here. 0, 6 hex. So serial, the first byte sent to SPI device is putting first a chip select down, and while chip select down is down, basically you run the clock and set the bits most significant bit first, 0, 0, 0, 0, 0, 1, 1, 0, end transmission. That wrote byte 0, 6 hexadecimal to the device. Okay, yeah, now it makes sense. And the same thing, I think this is the reading from the, or basically writing and reading. So chip select goes down. The first byte basically, this is the device. That data is the MOSI signal. So master sets byte, 05 for the system. Oh, wait a minute. Yes. And after that, that's the next byte sending 0, but this is what comes down. Okay, one thing about the SPI. The devices are actually, since there's only that one clock line, and it's so there's 2 data lines, and they are working actually simultaneously. So while you are writing, also the device is setting something for the MISO bus. Okay. And what it actually has here, that's what the device gave during the second byte. So this was the kind of command byte, and then the device answers. Something like that. Oops. Yeah, and PSOC has SPI, the slave, and then also it has a SPI master. Okay. So you can make this PSOC easily as a SPI slave, meaning that the for example, if you need to transfer some well, if the I2C is not fast enough for you, then use SPI to transfer the data from PSOC for example, to a Raspberry or some other device which doesn't have a good A to D converter. By the way, I think we are using the LPC Espresso on some of the Keijo Länsikunnas courses, and he just found out that this A to D is very crappy. So one way to replace the crappy A to D is have the PSOC crappy A to D and interface it with the SPI to the that LPC Espresso. Okay, good. So PSOC has SPI slave and master, and of course the APIs for those. Okay, one caution on using these devices. Let's go back to, for example, that one. This gap here, it's not actually due to the hardware, but the software. When you have transferred a byte, let's go to that one. Okay, these devices are all 8-bit, meaning that basically when you are shifting the data from that 8-bit register of this block to MISO or MOSI, you are also reading the read line on the same register. So it shifts bits out and gets the bits in at the same time. So it means that after you have made the 1 byte transfer, you need to go and read the whatever was on that register. Otherwise you will lose. Those hardware blocks don't have any buffers. Buffers you can do basically yourself by having this one to interrupt when the transmission is over, and then it goes and saves into buffer. But that's a software buffer. All right. Haha. That's nice. That's actually a data transfer between PSOC and that NRF24 wireless module. So this routine basically just reads 1 byte of that register on the 1 register of that radio module, and this one radio module uses SPI. So basically this block here is just LED module on PSOC. You turn that one to 0, so it's low active. Then basically this is to check that the transmission buffer of SPI master is empty. Okay, if it's empty, then it basically goes here, send data to SPI, and basically it's just the masked register and kind of the 1 byte with the bitwise, or Okay. And read register max with the address. Good. While okay, again, waits until the SPI module is ready. Send another data. If there was something with received from the device, it should have been read here. So when the SPI is complete, then you basically should have read that byte here. But well, this is just sending few bytes there, so it's the next sends that there. Then well, that's basically an empty payload. This is the command, and the answer to that command is the status register, but that's not the one what we would be reading. The next byte, while we are sending the zeros, actually would give the this register, like in here. So this could have been the first byte setting the command to that the device, and then next byte with the dummy output. This is what the device gives back. So that line here, that's the register value. Wow. And then end of transmission, and then return that byte. Okay. Distance extensions. So fundamentally, the SPI bus defines only the signals, not the levels or something like that. So in principle, you can extend these 4 lines by just adding some buffers, simple buffering, so that they can actually drive longer or more capacitive loads. So you can easily find these type 485 or 422 bus drives are technology from the 70s. So that was the extension of RS-232 up to 1 kilometer or so on twisted pair lines with quite poor balancing. But anyways, you can easily get, say, 100 meters or so. There are only the limits basically of the signal. Well, the biggest issue is the signal attenuation, and of course the capacitance kills the signal form. And then when you go really long lines, then you may actually have some, with high speed the return. So master out is always okay with the clock, since those are synchronized, but you may actually end up losing the phase shift with a very long lines, but that would mean kilometers of line and very high speed. Okay. Yeah, since let's see, in 100 nanosecond signal travels about 10 meters. So that's 10 megahertz. Okay. Well, you can always extend everything with optical, or use some, more robust technology like, 10 base T or 100 base, or what is that, 1000 base T. Optical things. Okay. Real bus. SPI summary. Synchronous full duplex bus short distance communication, and you can extend it with the drivers, and this says relatively high speeds. Actually, that's as high speed you need between circuits. There are devices with the SPI up to 100 megabits per second. And relatively easy with the PSOC. Yeah, nothing is really simple with the PSOC, but well, it's still much easier than writing your own code on some other system. And the difficulty, okay, all the devices have their own protocol. So the protocol, how to communicate with device are depending on the device manufacturer's mood. Okay, so that was the serial ports or serial communication on these devices. What was the title? Digital sensor interfaces. Yes. Okay. So OneWire, simple to connect, a little bit heavy on the this protocol side, although there are plenty of sample code to do it, and in PSOC there is a module to do it with all the APIs. Then the I2C, robust bus for, say, slower data transfer needs. Then the SPI when the speed really matters. The SPI is a little bit heavy on the. You need to really read the manual of the device really carefully. But I2C is more standardized. So there are more things standardized on the I2C, like the data transaction always starts with it, with this the data down, then clock down, the opposite way on the stop. Then every single transaction is initiated by the master by setting the address, 7-bit address with read or write. Okay, that's known. And then there are these two speeds, 100 kilobits and 400 kilobits devices. But I2C is a little bit, I would say that's a no-brainer, like as the SPI always needs some careful tweaking. Okay, anyhow, next week we'll have this exercise. So this week concentrate on these exercises 1 and 2. I will be here making sure that you can go forward if you have problems. And next week tutorial starts from the digital sensor interface exercise. Okay,